This video will examine the outputs of the DTFT and inverse DTFT when the input is constant. Let x of n be equal to the constant a for all n. Therefore, the output of the DTFT, capital X e to the j omega, is equal to a times the summation from n equals negative infinity to infinity of e to the negative j omega n. Simplifying this equation into something we can plot is not an easy task. For now, I'm just going to try to convince you of the answer, and then later we'll prove it using the inverse DTFT. The argument is as follows. Consider omega frozen as a constant. Note that the range of e to the j omega n is limited to values on the unit circle in the complex plane. Observe that if omega is set to pi over 2, the complex exponential is the sum of 1 plus I plus negative 1 plus negative I periodically over infinity, which is 0. This is true for most multiples of pi. Observe that if omega is set to a constant which is not a multiple of pi, the complex exponential will eventually take on all possible values on the unit circle, which of course will sum to 0. You may want to write a table in Excel or an algorithm in MATLAB to confirm this. Finally, consider the summation if omega equals a multiple of 2 pi, which includes 0. If omega is equal to a multiple of 2 pi, then the summation can be expanded as 1 plus 1 plus 1 plus 1, etc., which is an impulse of infinite height in area A. Therefore, we conclude that capital X e to the j omega is equal to a times the summation from k equals negative infinity to infinity of delta of omega minus 2 pi k. Let's plot the entire system. The input signal, x of n, is a series of stems of height a for all n. The output signal, capital X e to the j omega, is complex. We'll plot the signal in both polar and Cartesian coordinates, which is easy since they look the same. As usual, we only bother plotting over a 2 pi interval since we have previously proven that the output of any DTFT is 2 pi periodic. In part 1, I did a hand-waving argument for the output of the DTFT when the input is a constant. In part 2, we will prove this DTFT pair using the inverse DTFT. Given x of n equals a, I want to prove that capital X of e to the j omega is equal to a times summation from k equals negative infinity to infinity of delta of omega minus 2 pi k. First, recall the definition of the inverse DTFT. X of n is equal to 1 over 2 pi times the integral of capital X e to the j omega times e to the j omega n over a 2 pi interval with respect to omega. Plug in capital X e to the j omega. Note that because we integrate over a 2 pi interval, only one delta function in the summation will be included. Let's integrate over the integral from negative pi to pi so that we only care when k equals 0. Rewrite our equation as x of n equals a over 2 pi times the integral from negative pi to pi of delta omega times e to the j omega n d omega. Note that delta omega is equal to 0 for all values of omega except when omega is equal to 0. Plug in omega equals 0 into the equation and simplify. And we have proven that x of n is equal to a for all n. Let's examine what happens when we take the inverse DTFT of a constant. Plug the input signal, a, into the inverse DTFT equation and simplify, and we are left with a statement that x of n is equal to a if n equals 0 and 0 otherwise. Or equivalently, x of n is equal to a times delta of n. For me, this is a very strange result.